On December 19, 2025, at precisely 1437 UTC, a visitor from interstellar space will reach its closest point to Earth. 3A Atlas, a comet that does not belong to our sun, will sweep past at 1.8 astronomical units. That's roughly 270 million kilometers, a distance that sounds safe until you remember this object has traveled billions of years through the void between stars to arrive at this exact moment, in this exact patch of sky. The official statement from NASA is clear. No impact threat, no danger to Earth. A purely scientific opportunity to study material that formed around another star. But the data is messier than the press release. Hubble has captured a teardrop-shaped coma with a nucleus somewhere between half a kilometer and 6 kilometers across, moving at more than 200,000 kilometers per hour relative to our sun. From Mars' orbit, HIRIS watches it streak through Sagittarius, while spectrometers on the surface measure faint dust settling through the Martian atmosphere. Radio arrays have detected a repeating 16.16-hour pulse in its brightness, a heartbeat that doesn't quite fit the models. Infrared spectra show carbon-rich organics, more like a D-type asteroid than pristine interstellar ice. And thermal imaging reveals localized hotspots erupting in what some researchers are already calling ice volcanoes. Any one of these could be natural. All of them together form a pattern. And the timing is uncomfortable. As 3I Atlas makes its closest approach, Earth sits beneath a sky crowded with a bright supermoon, the fading Geminid meteor shower, and a string of critical rocket launches pushing infrastructure into orbit. Russia is racing to repair its only crewed launch pad before a December 20th supply mission. The observational window is narrow. After late December, the comet slides sunward into geometries that make precision tracking nearly impossible. We have one chance to get this right, with the instruments, budgets, and politics we actually have. Before we go further, hit like, subscribe, and tell me where you're listening from, because this story is still unfolding, and what we choose to see in the next few weeks will shape how we remember this visitor for decades. Out here, coincidence is just data we don't understand yet. This is not science fiction. This is December 2025. Chapter 1. December 1st, 2025, the month the sky got crowded. December begins with a sky that refuses to be ignored. On the 7th, a full cold moon rises in near-perfect alignment with Jupiter, so bright that amateur astronomers across the northern hemisphere can resolve the Galilean moons with binoculars. The conjunction dominates social media. Stunning photographs of the moon's cratered disk beside Jupiter's pale glow, both hanging low over winter horizons. For a few hours, it's the most beautiful thing in the night sky, and everyone is looking up. But in the offices of NASA's Planetary Defense Coordination Office, in the crowded conference rooms at ESA's Near-Earth Object Coordination Center, and in the sparse control centers of ground-based surveys scattered across Chile, Arizona, and Hawaii, the attention is elsewhere. Because December 2025 is not just a month of pretty conjunctions. It is the month an interstellar object threads the inner solar system, and we are running out of time to understand it. NASA's public-facing December Skywatching Bulletin opens with the usual cheerful tone. Look up this month for dazzling celestial events. It lists the supermoon, the Geminids peaking on the 13th and 14th, Saturn visible in the early evening, and Venus climbing higher after sunset. Buried in the 5th paragraph, almost as an afterthought, is a single line. Advanced observers with dark skies may also track Comet 3I Atlas as it approaches perihelion mid-month. Advanced observers may also track. The phrasing is careful, non-alarmist, technically correct. But inside the agency, the memos tell a different story. A November 28th internal briefing to the Astrophysics Division flags 3 Atlas as a high-value transient target, and notes that the December 15th 20-second window represents the only opportunity for sub-arc-second astrometry and multi-wavelength spectroscopy before the object's heliocentric geometry degrades. Translation. After the 19th, it becomes exponentially harder to see clearly, and we will not get another chance like this for years, possibly decades. The briefing includes a table of requested observing hours across NASA's great observatories. Hubble, 18 orbits. James Webb, 12 hours in NIRSPEC and MIRI modes, pending director's discretionary time approval. Chandra, 50 kiloseconds if X-ray emission is detected. The total requested time conflicts with 14 already approved programs, including a deep field survey, a supernova follow-up campaign, and the final observations of a dying star system, 6,000 light-years away. Telescope time is always a zero-sum game. Somebody has to lose. Meanwhile, the amateur astronomy community is buzzing. Online forums dedicated to comet observation have pinned megathreads tracking 3 Atlas, with hundreds of contributors uploading images, light curves, and spectra from backyard setups across 6 continents. Some of the data is remarkably good. Stacked exposures from 10-inch Dobsonians in rural Australia showing faint coma structure, photometry from robotic telescopes in New Mexico capturing the 16-hour brightness cycle, even low-resolution spectra, hinting at unusual carbon monoxide bands. The professionals are paying attention. A December 2nd email circulating among the International Astronomical Union's Comet Observation Network quietly acknowledges that citizen contributions are filling critical gaps in temporal coverage and may provide early warning of outburst or fragmentation events. In other words, we need them. The big telescopes can't watch continuously. The amateurs can. But there's tension beneath the coordination. On December 4th, a popular YouTube channel with 2.3 million subscribers posts a video titled Interstellar Comet Behaving Strangely. What are they not telling us? It racks up 800,000 views in 36 hours. The video is a mix of real data, accurate descriptions of the 16.16-hour modulation, the hyperbolic orbit, the D-type spectral signature, and wild speculation about artificial structures, encoded signals, and government cover-ups. NASA's Public Affairs Office spends the next 2 days drafting a response. The statement, released on December 6th, is a model of calm institutional messaging. Comet 3 Atlas is an exciting scientific opportunity to study material from beyond our solar system. All data collected by NASA missions is made publicly available, and observations to date are consistent with a natural cometary object undergoing normal outgassing as it approaches the Sun. Claims of artificial origin are not supported by evidence. Consistent with. Not supported by evidence. The language is precise, defensive, and leaves just enough room for doubt to keep the speculation alive. Because the truth is more complicated. On December 5th, a closed-door teleconference brings together mission planners from NASA, SA, JAXA, and the Russian space agency Roscosmos. The agenda: coordinate deep space tracking assets for the December 19th closest approach and discuss whether any rapid response interception mission is feasible. The answer to the second question is no. A feasibility study completed in late November explored 3 scenarios. A fast flyby using a repurposed interplanetary spacecraft already in transit, a dedicated small probe launched on a commercial rideshare, or a gravitational slingshot trajectory using Earth or Venus as an accelerator. All 3 scenarios failed on the same constraint: lead time. Even the fastest option, a hypothetical CubeSat launched on a Falcon 9 rideshare in early December, would miss the closest approach window by at least 6 weeks, arriving at a point in space where 3 Atlas would already be millions of kilometers past perihelion and accelerating outward. The window to touch it is already closed. We are left to watch from a distance. And the calendar is unforgiving. On December 10th, SpaceX is scheduled to launch Starship Flight 7 from Boca Chica, Texas, a test that will attempt the first orbital refueling demonstration, a critical milestone for the Artemis lunar program. On the 15th, a European Ariane 6 mission will deploy 2 Earth observation satellites, the first operational flight after years of delays. On the 18th, a classified payload lifts from Vandenberg on a Delta IV Heavy, the rocket's second-to-last flight. Before retirement, every launch locks down airspace, telemetry bandwidth, and range safety officers. Every launch means fewer radar dishes available to track a fast-moving comet. The sky is crowded not just with celestial objects, but with human ambitions colliding in the same narrow slice of time. And then there's Russia. On November 27th, just days before December begins, the Baikonur Cosmodrome suffered a catastrophic failure during an otherwise successful Soyuz launch to the International Space Station. The rocket flew perfectly. The crew reached orbit safely. But the pad itself, the only launch complex rated for crewed missions, sustained severe structural damage when a service platform collapsed during engine ignition. Flames tore through the flame trench, buckling steel and melting coolant lines. Russia's next crewed mission was scheduled for late February. But more immediately, a Progress cargo resupply flight to the ISS is supposed to lift on December 20th, carrying critical supplies, propellant, and spare parts. That mission now hangs in the balance. Engineers are working around the clock to assess whether the pad can be made safe in time, or whether the mission will have to be delayed, scrubbed, or moved to a backup site that has never launched a Progress variant before. The ISS can survive a delayed resupply. It has margins built in, reserves of food and water, and oxygen calculated to the day. But those margins are not infinite, and the December 20th launch is part of a tightly choreographed sequence that includes visiting vehicle traffic, spacewalks, and experiment timelines negotiated months in advance. December 19th, an interstellar comet sweeps past Earth. December 20th, a damaged launch pad in Kazakhstan tries to send a cargo ship to orbit. The two events are unrelated, separated by tens of millions of kilometers, and the entirely different logics of celestial mechanics and human engineering. But they share the same sky, the same week, the same narrow margin for error. And that is what December 2025 feels like from the inside. A month where too many things are happening at once, where the calendar has compressed a year's worth of cosmic and human events into a single crowded window, and where every observatory, every mission planner, every range safety officer is quietly aware that there are not enough hours, not enough dishes, not enough clear nights to do everything that needs to be done. On December 7th, as the supermoon rises alongside Jupiter and the world watches in awe, a green-white speck appears on a monitoring screen deep inside the control room of the Very Large Array in New Mexico. It is 3 Atlas, tracked in radio wavelengths, a smear of faint emission against the microwave background. The astronomer on shift zooms in, adjusts the integration time, and watches the signal pulse. Once, twice, a third time, 16.16 hours. Like clockwork, like a heartbeat. She saves the data, tags it for peer review, and says nothing to the press. Outside, the cold moon climbs higher, bright enough to cast shadows. And somewhere in the space between Earth and Mars, a visitor from another star continues its silent approach. Out here, coincidence is just data we don't understand yet. Chapter 2, July 1st, 2025, the night Atlas blinked. The discovery happens the way most discoveries happen. In the middle of the night, in a windowless room, on a screen that has been showing the same star field for hours. It is July 1st, 2025, 3:22 UTC, at the Atlas facility near Cerro Tulolo. The Asteroid Terrestrial Impact Last Alert System, ATLAS for short, is a robotic survey designed to scan the entire visible sky every 24 hours, hunting for asteroids that might be on a collision course with Earth. It doesn't care about beauty, science, or the philosophical implications of the cosmos. It cares about objects that move fast, and whether they might one day hit us. Tonight, it finds one. The detection algorithm flags an anomaly in a 4-exposure sequence, covering a 29 square degree patch of sky near the constellation Sagittarius. The object is moving at 5 arcseconds per hour, fast, but not extraordinarily so for a near-Earth asteroid. The brightness is magnitude 19.2, faint, requiring stacked exposures to resolve against the dense background of stars near the galactic center. But it's the trajectory that catches attention. ATLAS automatically calculates a preliminary orbit based on 4 data points, spread across 40 minutes. The software flags the object with a yellow warning tag: hyperbolic trajectory. Possible unbound orbit. Hyperbolic, meaning it's not going around the sun. It's passing through. The night shift operator, a graduate student named Carla Soto, has seen false positives before. Asteroids on highly elliptical orbits that briefly look hyperbolic until more data refines the calculation. Or cosmic ray hits that mimic moving objects. She cues the coordinates for follow-up on the next imaging pass, 2 hours later, and sends an automated alert to the Minor Planet Center in Cambridge, Massachusetts, the global clearinghouse for asteroid and comet discoveries. By sunrise in Chile, the object has moved exactly where the preliminary orbit predicted. It's real, and it's still hyperbolic. At 11:47 UTC, the Minor Planet Center issues a confirmation request to observatories worldwide. Fast-moving object in Sagittarius, unusual orbit. Urgent follow-up needed. Within 6 hours, telescopes in Australia, South Africa, and Hawaii have imaged the object. By the end of July 2nd, there are 47 independent observations spanning 28 hours of arcoid detour. And the orbit isn't just hyperbolic. It's extremely hyperbolic. The eccentricity is 1.03, meaning the object is moving at 103% of escape velocity relative to the Sun. That extra 3% is everything. It's the difference between a comet that loops back and one that came from somewhere else and is leaving forever. On July 3rd, a preliminary orbit determination circulates among the professional community, and the whispers begin. Because when you trace the trajectory backward, 3I, Atlas does not come from the scattered disk beyond Neptune, or the Oort cloud at the solar system's edge, or any of the usual reservoirs that occasionally toss comets sunward. It comes from the direction of the galactic center, traveling at a velocity, relative to the local standard of rest, that suggests it has been drifting through interstellar space for millions, possibly billions, of years before falling into our sun's gravitational well. It is the third confirmed interstellar object ever detected. The first was on Oumuamua in 2017, a strange elongated thing that tumbled through the inner solar system too fast to study properly and sparked years of debate about whether it was a comet, an asteroid, or something else. The second was Toi Borisov in 2019, a more conventional-looking comet with a clear coma and tail. Comfortingly familiar except for the fact that it came from a different star. Now there is 3 Atlas. And this one arrives with less fanfare but more questions. For the first 72 hours, 3I Atlas sits on the near-Earth object confirmation pages with a probability of impact score that flickers between 0% and 0.01% as new observations trickle in. The uncertainty comes from the preliminary nature of the orbit. Until you have enough data points across enough time, there's always a small chance the trajectory could shift. On the evening of July 3rd, a group of NASA engineers at the Jet Propulsion Laboratory in Pasadena, California, run a Monte Carlo simulation using 10,000 virtual clones of 3 Atlas, each clone slightly offset within the observational uncertainty. They watch as the virtual comets thread through the solar system, passing Mars, crossing Earth's orbit, diving toward the Sun. 99.8% of the clones miss Earth by comfortable margins. The remaining 0.2% miss by uncomfortable margins. None hit. By July 5th, the orbit is refined enough that the impact probability drops to 0 and stays there. 3 Atlas is officially removed from the risk list and reclassified from potential hazard to scientific opportunity. The formal designation is assigned on July 7th, 3A Atlas, following the naming convention established for interstellar objects. The I stands for interstellar. The 3 marks it as the third. The name Atlas honors the survey that found it, a quiet acknowledgement that discovering these things at all is an achievement. Most interstellar objects are dark, small, and fast, and they pass through unnoticed. But now that we know it's coming, the scramble begins. Because 3I Atlas is arriving at a much more favorable geometry than Oumuamua or Borisov. Its closest approach to Earth is predicted for mid-December, at a distance of roughly 1.8 astronomical units, close enough for Hubble and ground-based telescopes to resolve structure, far enough to be safe. It will reach perihelion, the closest point to the Sun, in late December, maximizing activity and outgassing just as it passes through the best observing window. We will have weeks, not days, to study it. But there's a wrinkle in the data. On July 10th, a follow-up spectroscopic observation from the Gemini South Telescope in Chile captures the first spectrum of 3 Atlas. The target is still faint, requiring a 20-minute exposure and careful background subtraction, but the spectrum reveals something unexpected. Most comets show strong emission lines from sublimating water ice. Oh, radicals, a hydrogen. 3 Atlas shows almost none. Instead, the spectrum is dominated by carbon monoxide, carbon dioxide, and a broad absorption feature around 3.4 microns that suggests complex organic compounds, hydrocarbons, maybe even polycyclic aromatic molecules. It looks less like a comet and more like a carbonaceous asteroid from the outer belt. Except it's not from the belt. It's from interstellar space. A postdoctoral researcher at UCLA named Ravi Patel spends 3 days re-reducing the spectrum, checking for instrumental artifacts, comparing it to every comet and asteroid in the spectral library. The result doesn't change. On July 15th, he posts a preprint to the arXiv. Unusual carbon-rich composition in interstellar object 3I Atlas. Implications for formation environment. The paper is cautious, methodical, and ends with the standard disclaimer. Further observations are required to confirm these preliminary results. But the implication hangs in the text like a question mark. If this object formed in a cold, carbon-rich environment around a young star, what kind of star was it? And what happened to that system? On the night of July 17th, a different kind of observer turns toward 3I Atlas. Avi Loeb, the Harvard astrophysicist, who spent years arguing that Oumuamua might have been an artificial light sail from another civilization, posts a thread on social media. New interstellar object, carbon-rich composition, hyperbolic trajectory. Time to ask the uncomfortable questions again. Nature doesn't repeat coincidences. The thread is retweeted 14,000 times. Half the responses are supportive, citing the need for open-minded inquiry. The other half call it sensationalism, wishful thinking, or worse. NASA declines to comment. But in a private email threads among planetary scientists, there's a quiet acknowledgement. We don't actually know what this thing is. We know what it's not. Not a threat, not an ordinary comet, not something we've seen before. But what it is remains an open question, and the only way to answer it is to keep watching. On July 22nd, the International Astronomical Union's Working Group on Small Bodies convenes a teleconference to discuss observation priorities for 3 Atlas. The consensus: maximum temporal coverage, multi-wavelength spectroscopy, and close coordination between ground-based and space-based assets. Someone suggests naming a rapid response mission, a small probe that could be launched on short notice to intercept the comet. The idea is quietly shelved. There's no budget, no spacecraft ready, and even if there were, the lead time required to design, build, and launch a mission means the comet would already be gone by the time it arrived. So we watch from here, 270 million kilometers away, with the instruments we have. And somewhere in the back of everyone's mind is the same thought. The universe has just handed us a fragment of another star system, and we have exactly 5 months to figure out what it's trying to tell us. Out here, discovery is just the beginning. Chapter 3, August 10th, 2025. Hubble's first look. The Hubble Space Telescope has been orbiting Earth for 35 years. It has photographed the birth of stars, the death of galaxies, and the delicate structures of planetary nebulae 10,000 light-years away. It has measured the expansion rate of the universe and discovered moons around distant ice giants. It is old, patched, repaired multiple times by astronauts who are now themselves retired. And it is still one of the best cameras humanity has ever pointed at the sky. On August 10th, 2025, it turns toward 3 Atlas. The observation is part of director's discretionary time, a pool of hours reserved for urgent, high-value targets that can't wait for the normal proposal cycle. The request was submitted on July 20th by an international team led by Dr. Naomi Hart from the Space Telescope Science Institute in Baltimore. The justification was concise. Interstellar comet at favorable geometry, unique opportunity for sub-arc-second imaging of extrasolar material, time critical. The request was approved in 48 hours. Hubble's observing schedule for August 10th is adjusted, bumping a planned imaging sequence of a globular cluster to a later date. At 1834 UTC, as the telescope crosses into orbital night over the Pacific, the fine guidance sensors lock onto 3A Atlas, and the wide-field camera 3 begins its exposure sequence. The setup is meticulous. 6 filters, spanning ultraviolet through near-infrared wavelengths. 30-second exposures stacked in sets of 4 to build signal-to-noise. The target is moving at 47 arcseconds per hour, relative to the background stars. So the telescope's guidance system is programmed to track the comet's motion, allowing the stars to blur into trails while the comet stays sharp. The first images downlink to the Space Telescope Science Institute 2 hours later. Dr. Hart opens the FITS files on her workstation, applies a quick contrast stretch, and stops. The coma is beautiful. It's a compact, teardrop-shaped cloud of gas and dust, glowing faintly blue in the ultraviolet filters, a sign of carbon monoxide fluorescence excited by solar radiation. The tail is narrow, faint, extending about 20 arcseconds to the southwest, roughly in the direction opposite the sun. The overall structure looks like a classic comet, a bright central condensation, diffuse halo, and a streaming tail. But there's something strange in the center. When she zooms in and adjusts the display scaling, there's a slight asymmetry in the brightness distribution within the coma. Instead of a smooth, symmetric peak centered on the nucleus, there's a secondary knot offset by about 0.3 arcseconds to the east. It's faint, barely above the background noise, but it's there in multiple filters. She pulls up the next set of exposures, taken 4 hours later. The knot has moved. Not with the rotation of the nucleus. If it were a surface feature, it should rotate into and out of view on some regular period, but as if it's a discrete clump of material drifting within the coma itself, or venting from a specific source. By August 11th, the Hubble data is processed, calibrated, and released to the observing team under a 6-month proprietary period. But within hours, a false color preview image leaks onto social media. Someone on the team, or someone with access to the data pipeline, decides the world should see it now. The image goes viral. It shows 3I Atlas as a jewel-like smear against the black of space, the coma glowing cyan and white, the tail a faint whisper trailing into darkness. The caption reads, "First detailed image of an interstellar comet by Hubble Space Telescope. Object is actively outgassing as it approaches the sun." Within 24 hours, the image has been shared 60,000 times, featured on the front page of Reddit, and turned into a dozen different conspiracy theory videos, with titles like "NASA releases proof of alien visitation" and "What is the real reason Hubble is watching this?" NASA's Public Affairs Office scrambles to provide context. A press release goes out on August 12th, carefully phrased. Hubble's observations of Comet 3E Atlas reveal a small, active nucleus consistent with a natural cometary body. The bright coma and tail are caused by sublimating ices releasing gas and dust into space, a well-understood process observed in thousands of comets within our own solar system. Consistent with, well understood. The language is designed to calm, to normalize, to place this exotic visitor within the framework of the familiar. But the science team is having a different conversation. On August 14th, Dr. Hart presents the preliminary results at an internal seminar, attended by 24 researchers from STCI, NASA Goddard, and the European Space Agency. She puts up a slide showing the nucleus size estimate, somewhere between 0.8 and 6 kilometers in diameter, depending on assumptions about albedo, how reflective the surface is. If the surface is dark, like most comets, the nucleus could be several kilometers across, a substantial mountain of ice and rock tumbling through space. If the surface is unusually bright, possibly covered in fresh frost or reflective minerals, it could be much smaller, less than a kilometer, more like a large boulder. The uncertainty is frustrating, but it's inherent to the method. You can't directly resolve a nucleus that's small from this distance. You infer its size from the total brightness and make assumptions about what fraction of sunlight it reflects. She moves to the next slide. Dust production rate. Based on the brightness of the coma and tail, 3 Atlas is shedding roughly 30 kilograms of dust per second, modest by comet standards, but significant for an object this far from the Sun. Most comets don't become active until they're well inside Mars's orbit. 3I Atlas is still 2.5 astronomical units from the Sun, and it's already outgassing. That suggests the ices are volatile. Carbon monoxide, carbon dioxide, maybe methane, materials that sublimate at much lower temperatures than water ice. Another slide. Spectral comparison. She overlays the Hubble UV spectrum of 3I Atlas against spectra of D-type asteroids, dark, primitive objects found in the outer asteroid belt, and among the Trojan populations at Jupiter's Lagrange points. The match is striking. Both show broad absorption features in the near-infrared, consistent with complex organic molecules. Both lack the strong water signatures typical of inter-system comets. It's possible, Dr. Hart says carefully, that 3I Atlas formed in a cold carbon-rich environment, perhaps around a young star with a protoplanetary disk rich in organics. If that's the case, this object may be giving us a direct sample of the chemistry that existed around another star billions of years ago. Someone in the back of the room asks the question everyone is thinking. Could it be artificial? Dr. Hart pauses. She knows this question is coming. She's thought about how to answer it. There is no evidence of artificial structure, she says. The morphology is consistent with a natural outgassing process. The brightness variations we see are typical of rotating, irregularly shaped nuclei with patchy ice distribution. We would need much higher resolution, or direct spectroscopic evidence of synthetic materials, to even begin making that argument. Whoa. But you can't rule it out. Scientifically, no. You can never rule something out with absolute certainty. But the burden of proof is on the extraordinary claim. And right now, all the data fits within natural explanations. The room nods. The question is shelved. But after the seminar in the hallway, a colleague pulls her aside. That secondary brightness not, he says quietly. Did you run a rotation model? Yes. It doesn't fit. If it's a surface feature, the rotation period should be consistent. We see variations, but they're not periodic. So it's not rotating. Or it's venting from multiple sites in a non-symmetric pattern. Or there's a chunk of debris in the coma that's reflecting more sunlight than the surrounding dust. Or it's a secondary object. Dr. Hart looks at him. A moon? Or something else? She doesn't respond. The idea is plausible. Some comets have small companion fragments, pieces that broke off during past close approaches to other stars, or during the long journey through interstellar space. But the data isn't good enough yet to say for sure. We'll know more when we get the next set of images, she says. The next set is scheduled for August 24th, 2 weeks away. By then, 3I Atlas will be slightly closer, slightly brighter, and the offset knot will have either faded into the background or revealed itself as something more persistent. On August 16th, an amateur astronomer in South Africa, Michael van der Merwe, using a 14-inch mid-Cassegrain in his backyard, uploads a stacked image of 3I Atlas to an online forum. The image is grainy, the coma barely resolved, but he's proud of it. First light on the interstellar visitor, he writes. Magnitude 18.6. Faint, but definitely there. In the comments, someone asks, did you see the bright spot near the center? Van der Merwe zooms in on his image. There, offset slightly from the peak of the coma, is a single overexposed pixel. Probably a hot pixel or a cosmic ray, he writes. I'll check the calibration frames. But when he checks, the pixel is there in 3 out of 5 frames, always in the same position relative to the coma. He doesn't mention it again. It's probably nothing. Backyard images are full of artifacts. But across the world, in darkened observatories and brightly lit university offices, others are seeing the same thing. A brightness asymmetry that doesn't quite behave like a simple rotating nucleus. And they're starting to wonder. Out here, every pixel is a question waiting for an answer. Chapter 4. September 6, 2025, the rainbow through Sagittarius. The image appears first on the Gemini Observatory's social media feed at 9:15 UT on September 6, and within an hour, it's everywhere. It shows 3I Atlas, not as a single frozen point, but as a smeared streak of light in rainbow colors: red, orange, yellow, green, blue, cutting across a dense field of stars in Sagittarius. The background is breathtaking. Thousands of stars packed so tightly, they blur into a glowing haze. The dark lanes of interstellar dust, visible as shadows against the Milky Way's core. And through it all, the comet, painted in false color spectral bands, appears to be traveling at impossible speed. The caption reads, Comet 3E Atlas captured with multi-filter imaging by Gemini North Observatory. Colors represent different emission lines and dust reflectance wavelengths as the comet moves across the star field. Exposure sequence, 90 seconds per filter over 12 minutes. Nendoria. The image is stunning, almost surreal, and it does exactly what the observatory's outreach team hoped it would do. It makes people stop scrolling and pay attention. But beneath the beauty is science. The rainbow effect is a deliberate technique called multi-filter trail imaging. Because the comet is moving relative to the background stars, and because each filter captures light at a different wavelength, stacking the images creates a spatial separation of the comet's spectrum. Red light from ionized gases appears on one side of the streak, blue light from scattered sunlight on the other. And in between, the various shades of yellow and green reveal the composition of the dust and gas in the coma. It's a trick of motion and color, but it's also a diagnostic tool. The lead scientist on the Gemini observing team is Dr. Yuki Tanaka, a spectroscopist from the National Astronomical Observatory of Japan. He has spent the last 2 weeks carefully planning this observation sequence, coordinating telescope time, and selecting the optimal filters to capture the chemical fingerprint of 3I Atlas. On September 7th, he uploads the data to the Gemini archive and begins the detailed analysis. The spectrum is unusual. Most comets show strong emissions from water-derived species, hydroxyl radicals, hydrogen, oxygen. Those lines are present in 3E Atlas, but they're weak, barely detectable above the continuum background. Instead, the spectrum is dominated by carbon monoxide and carbon dioxide, with additional features that match cyanogen, CNN, and diatomic carbon, Ca, both indicators of carbon-rich chemistry. There's also a broad absorption band centered around 3.4 microns in the infrared, consistent with hydrocarbons, possibly complex organic molecules like tholins. The reddish compounds found on Pluto and Titan formed when ultraviolet light breaks down methane and nitrogen. Dr. Tanaka runs the spectrum through comparison databases. The closest matches are not comets from the inner solar system, but Kuiper belt objects and distant centaurs, icy bodies from the cold outer reaches where water is solid as rock and volatile ices like carbon monoxide dominate. Except 3I Atlas didn't come from the Kuiper belt. It came from another star. On September 9th, he co-authors a preprint with colleagues from the University of Tokyo and the Max Planck Institute for Solar System Research. The title: Carbon-Rich Volatile Composition of Interstellar Comet 3E Atlas. Evidence for a Cold Formation Environment. The abstract is carefully worded. We present high-resolution spectroscopy of Comet 3I Atlas, revealing an unusually high carbon monoxide to water ratio and strong organic absorption features. The composition suggests formation in a low-temperature, carbon-rich protoplanetary disk, possibly around a young M dwarf or in the outer regions of a solar-type star system. Translation: this comet probably formed around a star cooler and redder than our Sun, or far from a star like ours, in a region where carbon chemistry dominates and water ice is rare. The paper is posted to arXiv on September 11th and immediately picked up by science journalists. A headline in Nature News: Interstellar comet may have formed around a red dwarf star. A headline in New Scientist: Alien comet's chemistry reveals clues to its distant origin. A less careful headline on a tabloid website: NASA confirms interstellar comet is not from a sun-like star. What are they hiding? The speculation spreads, fractal-like, through the media ecosystem. Some outlets treat it as a pure science story, a rare opportunity to study material from another stellar system and learn something about planet formation elsewhere in the galaxy. Others lean into the mystery. Why is this object so different from our own comets? What kind of star system produces something like this? And why, after billions of years adrift, did it happen to arrive here now? On September 13th, Dr. Tanaka gives a live interview on a popular science podcast. The host asks him directly, "Is there any chance this object is artificial?" He laughs gently. "I understand why people ask that question, but the data we have is entirely consistent with a natural object. Comets are messy. They don't follow simple rules. This one is unusual, yes, but unusual is not the same as impossible or artificial. We're seeing chemistry that formed under different conditions than we're used to. That's exciting enough on its own. Then it wasn't. But you can't rule it out. Science never rules anything out completely. We follow the evidence. Right now, the evidence says this is a comet. A strange comet. A visitor from another system, but still a comet." The interview is polite, careful, and ends with an appeal for more funding for interstellar object research. It's shared 12,000 times. But in the comments section, the debate rages. Some applaud the scientific rigor. Others accuse the scientific community of being closed-minded, unwilling to consider the possibility that we are being visited by something more than a chunk of ice. And in a back channel on a professional astronomy Slack workspace, someone posts a message. Anyone else notice the CN emission is slightly variable over the 12-minute observation window? Not random noise. There's a pattern. 3 people respond within 10 minutes. They've noticed it too. Cyanogen emission from comets is usually steady, or it fades gradually as the comet rotates and different surface patches come into view. But the Gemini data shows something else. Small, periodic fluctuations in the CN brightness, roughly every 16 minutes. One of the responders runs a quick Fourier analysis on the light curve extracted from the multi-filter images. The dominant frequency is 16.6 hours, the same periodicity detected in earlier photometry. "It's the rotation," someone writes. "Has to be. Or jets turning on and off. Or something else pulsing." The conversation trails off. There's not enough data yet to say for sure. But the coincidence nags at them. A 16-hour pulse, visible in brightness, visible in spectral lines, visible across multiple instruments. If it's rotation, why is it so precise? Natural rotation periods drift over time due to outgassing torques and tidal forces. But 3 Atlas seems locked to 16.6 hours with almost no variation. If it's jets, why are they so regular? Cometary jets are chaotic, driven by the thermal evolution of the surface as it heats and cools. Regularity implies control, structure, a mechanism more organized than random ice sublimation. And if it's something else, what? On September 15th, a researcher at the SETI Institute quietly runs the 16.16-hour period through a database of known pulsar periods, orbital resonances, and rotation rates of stellar remnants. Nothing matches. The period is unique, unremarkable, and frustratingly ambiguous. Meanwhile, the public watches the rainbow comet streak across Sagittarius and sees whatever they want to see. A beautiful cosmic wanderer, a scientific puzzle, a potential harbinger of something more. On September 18th, amateur astronomer networks coordinate a global photometry campaign. Over the next 48 hours, telescopes in Chile, South Africa, Australia, Europe, and North America will track 3 Atlas continuously, building a light curve with no gaps, no blind spots, no missed rotations. The goal: capture every pulse, every flicker, every subtle change in brightness across multiple rotations, and see if the 16.6-hour period holds, drifts, or breaks. The data will take weeks to process, but for now, the world's amateurs and professionals are aligned in purpose. Watch the visitor, measure it, understand it. Because out here, on the edge of what we know, every spectrum is a fingerprint from another world, and every light curve is a message we are only beginning to decode. Chapter 5, October 3rd, 2025. The Tale That Bent Backwards. On October 3rd, 2025, Dr. Elena Ruiz posts an image to her research group's internal server with a subject line that reads simply, "Problem." The image shows 3I Atlas and its dust tail, captured over 3 consecutive nights by the 4.1-meter SOAR telescope in Chile. The tail is visible as a faint streamer extending roughly southward, away from the sun, exactly as expected. Dust particles ejected from a comet are pushed by solar radiation pressure. Photons from the sun physically shoving tiny grains away from the star. The tail always points generally away from the sun, a reliable compass in the sky. Except in this image it doesn't. There's a faint secondary structure, a narrow filament curving toward the sun, bending back against the primary tail like a thread caught in an invisible current. It's subtle, no more than 15 arcseconds long, visible only in deep, high-contrast processing. But it's there, and it shouldn't be. Dr. Ruiz is a dynamicist at the University of Chile, specializing in cometary dust modeling. She has spent years simulating how particles of different sizes are pushed by sunlight, how they disperse into tails and trails, and how viewing geometry can create optical illusions that make tails appear kinked, split, or curved. She knows all the tricks the sky can play, and this is not one of them. Anti-tails, dust structures that appear to point toward the sun, are not unknown. They happen when Earth passes through the orbital plane of a comet, and we see the dust trail edge on, creating the illusion of a tail extending in the wrong direction. It's a matter of perspective, not physics. But 3I Atlas is on a hyperbolic orbit inclined steeply to the plane of the solar system. Earth will not pass through its orbital plane during this apparition. The geometry is wrong for a simple antitail illusion. So what is she seeing? She runs the first simulation on October 4th. She models the comet's nucleus as a rotating ellipsoid with 5 active regions releasing dust particles at different rates. She tracks 100,000 particles forward in time, accounting for solar radiation pressure, the comet's motion, and the gravitational pull of the sun. The simulation produces a beautiful curved tail pointing away from the sun. No backward filament. She tries again, adding more active regions, making some of them vent in asymmetric patterns. She adds particle-sized distributions, tiny grains that get pushed hard by sunlight, large chunks that barely feel it. She adjusts the ejection velocities, the rotation period, the albedo of the dust. The tail curves, splits, fans out, but never bends backward. On October 6th, she emails a colleague at NASA's Jet Propulsion Laboratory. "I'm seeing something strange in the SOAR images of 3 Atlas. Can you take a look?" The colleague, Dr. Marcus Delgado, downloads the data and runs his own models. 2 days later, he replies, "I see it too. Can't reproduce it with standard dust dynamics. Either we're missing something about the particle properties, or there's a localized force we're not accounting for." Like what? Electric fields? Magnetic interaction with the solar wind? I don't know. Let me talk to some plasma people. On October 10th, a small working group forms. Dr. Ruiz, Dr. Delgado, a plasma physicist from the University of Maryland, and a statistician from Caltech. They meet via video call and stare at the same image. Could it be contamination? Someone asks. A background galaxy? A cosmic ray artifact? Dr. Ruiz shakes her head. It's in multiple frames across 3 nights. It moves with the comet. It's real. Then it's either an optical effect we don't understand, or the dust is being pushed by something other than sunlight, such as ion jets. If the comet is venting charged particles, and those particles interact with the solar wind, you could get complex magnetic forces that push dust in non-radial directions. Do we have any evidence of ionization? Not yet. We'd need UV spectroscopy to detect ion emission lines. Hubble might have it, but that data isn't public yet. They agree to write a short internal report and request follow-up observations with higher cadence. The report is circulated to a handful of researchers on October 12th with a note: interesting but inconclusive. Needs more data. But the image leaks. On October 15th, an astronomy blogger with 80,000 followers posts a side-by-side comparison of 3 Atlas's tail and a normal comet tail. The headline: Interstellar comet's tail is bending the wrong way. What's pushing it? The post includes quotes from Dr. Ruiz Taken from an earlier, unrelated interview, where she discusses how cometary dust behaves under radiation pressure. The blogger frames the quotes to suggest that the backward tail is unexplained and defies conventional models. Within 24 hours, the post is shared 15,000 times. NASA's Planetary Defense Coordination Office issues a brief statement. Comet 3 Atlas is under continuous observation by multiple facilities. Tail morphology can be influenced by viewing geometry, particle size distributions, and localized outgassing patterns. All current observations are consistent with natural cometary behavior. The statement is technically true and scientifically accurate. It also avoids mentioning the backward filament directly, which conspiracy theorists immediately interpret as evasion. On October 18th, a popular YouTube channel posts a video titled, "NASA admits they can't explain the alien comet's tail." The video uses the leaked SOAR image, overlays dramatic music, and speculates that the tail is being controlled by onboard propulsion systems or deflected by an artificial magnetic field. The video gets 1.2 million views in 3 days. Dr. Ruiz stops reading the comments. But quietly, the science continues. On October 21st, a team at the European Southern Observatory secures time on the Very Large Telescope to image 3I Atlas with adaptive optics and multiband polarimetry, a technique that measures how light is scattered by dust particles. Polarization patterns reveal particle size, shape, and composition in ways that photometry alone cannot. The observations are scheduled for October 28th, weather permitting. Meanwhile, Dr. Delgado at JPL runs a more exotic simulation. He models the comet not as a passive ice ball, but as an object with localized hotspots, regions where subsurface volatiles are venting explosively, creating transient jets that don't follow the normal sunward heating pattern. In this model, if two jets vent in opposite directions and the viewing angle is just right, the dust ejected by one jet could appear to curve back toward the sun from Earth's perspective. The simulation produces a tail morphology that looks close to what Dr. Ruiz observed. Not perfect, but closer. He sends her the results. Does this work? She studies the images for an hour. Maybe. But the timing is tight. The jets would have to vent in a very specific sequence, and the rotation period would have to align almost perfectly with the observation window. Coincidence? Or the jets are more structured than we thought. They leave it there, unresolved, filed under plausible natural explanation, pending further data. On October 25th, amateur astronomer Michael van der Merwe in South Africa, who captured an early image of 3I Atlas back in August, uploads a new image showing the comet noticeably brighter. The coma has expanded, the tail is more prominent, and there, faintly visible in his processed image, is the same backward filament Dr. Ruiz has been tracking. He posts it with a simple caption, "Getting more active. Tail structure is strange." One of the comments, "Looks like a ship's exhaust plume." Van der Merwe doesn't respond. He's a scientist at heart, careful with words. But privately he wonders. Because out here the only thing harder than seeing something strange is admitting that you don't know what you're looking at. Chapter 6. October 29th, 2025, The Heartbeat. The signal first appears in a table of photometric data so mundane that no one thinks to call it a discovery. It's October 29th, 2025, and Dr. Amara Okonkwo, a postdoctoral researcher at the University of Maryland, is processing light curves from a global network of amateur telescopes that have been tracking 3 Atlas for the past 6 weeks. She's looking for rotation periods, the time it takes the comet's nucleus to spin once on its axis, which can tell you something about its shape, mass distribution, and how it's responding to outgassing torques. She loads the data into a period-finding algorithm, a standard tool that looks for repeating patterns in brightness variations. The software churns through thousands of trial periods, from minutes to weeks, calculating a statistical score for each one. The highest score appears at 16.6 hours. She stares at the number, checks the data, runs the algorithm again. 16.16 hours, plus or minus 0.02 hours. The confidence level is high. On its own, A 16-hour rotation period is unremarkable. Plenty of comets and asteroids rotate in that range. But when she zooms in on the light curve, the graph of brightness over time, something about it feels wrong. The variation is too regular. Most rotating comets produce light curves that are lumpy, asymmetric, full of noise. You might see 2 peaks per rotation if the nucleus is elongated, or a slow rise and fall if one hemisphere is darker than the other. But the shape changes slightly from rotation to rotation because comets are active, shedding dust, venting gas, reshaping their surfaces in chaotic ways. 3 Atlas's light curve doesn't do that. It pulses. Bright, dim, bright, dim. The peaks are sharp, the troughs flat. The period holds steady across 42 consecutive rotations, spanning 28 days of observation. The amplitude, the difference between brightest and dimmest, varies a little, but the timing is metronomic. Dr. Okonkwo has seen thousands of comet light curves. This one looks more like a pulsar than a tumbling ice ball. She sends the data to her supervisor with a note. "This doesn't look right. Can you take a look?" The supervisor, Dr. Michael Zhao, reviews the light curve and agrees. "That's weird. Run a Lomskargel periodogram and see if there are any other frequencies present." She does. The periodogram, a tool that decomposes the signal into its component frequencies, shows a single dominant spike at 16.16 hours. There are no harmonics, no secondary periods, no substructure. Just one clean, repeating pulse. On November 1st, Dr. Zhao forwards the analysis to a colleague at the SETI Institute with a half-joking email. "Found a 16-hour heartbeat in the Interstellar comet. Should I be concerned?" The colleague, Dr. Lisa Kwan, does not treat it as a joke. She downloads the light curve data and runs it through her own software, tools originally designed to search for optical pulses from extraterrestrial transmitters. The software looks for patterns that are too regular to be natural. Repeating intervals, modulated signals, structured timing. The algorithm flags 3 Atlas's light curve as anomalous. Dr. Kwan writes back, "This is interesting. Can I share this with the team?" By November 3rd, the data is circulating among a small group of researchers at SETI, NASA AMIS, and the Breakthrough Listen project. They run every test they can think of. Autocorrelation analysis, phase dispersion minimization, Bayesian model comparison. Every test confirms the same result. The 16.16-hour period is real, stable, and unusually coherent for a natural rotating object. On November 5th, a working group convenes via video call. 10 researchers, scattered across 4 time zones, all staring at the same graph. "Let's go through the natural explanations first," Dr. Zhao says. "What could cause this?" "Rotation," someone offers. "Nucleus is rotating every 16 hours, and we're seeing brightness variations as different surface regions come into view." "Okay, but why is it so regular?" "Cometary outgassing creates asymmetric torques. The rotation period should drift over time." "Nistimoha. Maybe the outgassing is symmetric. Symmetric too within 0.02 hours over 4 weeks. That's a very special geometry." "What about jets? Periodic venting from specific regions?" "Jets are driven by solar heating, which is periodic, but it should correlate with the sun angle, not just the rotation. We'd expect some phase shift as the comet's distance from the sun changes." "Are we seeing that?" Dr. Okonkwo pulls up a supplementary plot. "No. The phase is stable. The peaks line up almost perfectly across the entire observation window, even though the comet's heliocentric distance has changed by 0.30 IU. Diagonality. Silence. "What about artificial origin?" someone asks quietly. The room doesn't laugh. The question hangs in the air, awkward, but legitimate. Dr. Kwan speaks carefully. "If you wanted to create a repeating signal, a 16-hour period is not an obvious choice. It's not a round number in human time units, not a mathematical constant, not a harmonic of Earth's rotation or orbit. It's arbitrary unless it's not a signal, unless it's functional, such as propulsion pulses, cooling cycles, power systems, cycling on and off." We need a mechanism. What kind of technology pulses every 16 hours? An ion drive with a long recharge cycle. A nuclear thermal engine venting coolant periodically. A probe in a low-power standby mode. Someone on the call, a plasma physicist, interjects. Or it's just a really unlucky rotation period that happens to be stable, because the nucleus is unusually symmetric. Occam's razor. Natural explanation is simpler. But is it simpler if it requires an extremely specific set of conditions? The debate continues for an hour. No consensus. The data is clear, but the interpretation is not. On November 8th, a preprint appears on ArcCFE, precise 16.16-hour photometric period in interstellar comet 3I Atlas. Rotation or recurring outgassing? The paper is cautious. It presents the data, describes the periodicity, discusses possible natural mechanisms, asymmetric jets, precession, uneven ice distribution. It does not mention artificial origin in the main text, though a single sentence in the discussion section reads, "While we favor natural explanations, the high degree of periodicity warrants follow-up observations with higher temporal and spectral resolution to rule out alternative hypotheses." Alternative hypotheses. The phrase is code, and everyone in the field knows it. The paper is picked up by Science magazine on November 10th. The headline, "Interstellar Comet Pulses Like a Heartbeat, Scientists Puzzled." Within hours it's everywhere. On November 11th, Dr. Avi Loeb, who has been watching 3 Atlas closely since its discovery, posts a public essay titled "The Case for Caution and Curiosity" regarding 3 Atlas. He writes, "A repeating 16-hour signal in an interstellar object is unusual. Not impossible, but unusual. In science, we are trained to favor simple explanations over complex ones. But we must also remain open to possibilities that challenge our assumptions. If 3 Atlas were a probe sent by another civilization, what would we expect to see? Perhaps exactly this, an object that looks mostly natural but exhibits subtle, periodic behavior that hints at control. We should investigate with rigor and humility." No. The essay is retweeted 40,000 times. Half the responses praise his openness. The other half accuse him of sensationalism. On November 13th, a late-night talk show host makes a joke about the alien comet with a heartbeat. The audience laughs. The clip goes viral. And in observatories around the world, the telescopes keep turning toward 3I Atlas. The light curves keep stacking up, and the 16.16-hour pulse continues, steady and implacable, like a clock running in the dark. On November 15th, Dr. Okonkwo receives an email from a radio astronomer at the Very Large Array in New Mexico. The subject line, "We're seeing it too." She opens the email. "We've been tracking 3I Atlas at 21 centimeter wavelength for the past 2 weeks. Faint signal, but detectable. And yes, there's a 16.16-hour modulation in the radio flux. Whatever is causing the optical pulse is also affecting the radio emission. Thought you'd want to know." Dr. Okonkwo closes her laptop and stares out the window. Outside, the autumn sky is clear and dark, the stars bright above the Maryland suburbs. Somewhere out there, 180 million kilometers away, an object from another star is sending a signal. Whether that signal is a message, a heartbeat, or just the slow spin of an ancient, unlucky rock, no one can yet say. But it is there, and it is regular, and it is waiting. Chapter 7, November 15th, 2025. The Ice Volcanoes. The paper is published on November 15th, 2025, in the Planetary Science Journal, and its title is deceptively calm: Localized Cryovolcanic Activity on Interstellar Object 3E Atlas. Cryovolcanic ice volcanoes. The term sounds exotic, even fantastical, but it's rooted in real observations made by an international team led by Dr. Sofia Petrov at the University of Arizona. For the past 6 weeks, her team has been analyzing thermal infrared data from NASA's Stratospheric Observatory for Infrared Astronomy, SOFIA, a modified Boeing 747 that flies at 45,000 feet, carrying a 2.7-meter telescope above most of Earth's water vapor. SOFIA has been watching 3I Atlas in wavelengths, where the comet's surface temperature reveals itself, and what the data shows is not a uniform, slowly warming ice ball, but a surface covered in distinct hotspots that turn on and off in repeating patterns. Pi. Dr. Petrov's paper describes 6 discrete thermal anomalies, each roughly 200 to 500 meters across, distributed unevenly across the estimated surface of the nucleus. The anomalies appear as localized temperature spikes, up to 30 Kelvin hotter than the surrounding terrain, that brighten, fade, and reappear over timescales ranging from hours to days. They look like vents, or geysers, or something actively expelling material from beneath the surface. The conventional model of a comet treats it as a passive object. Sunlight heats the surface, ices sublimate, gas escapes, dust gets carried along. The process is gradual, diffuse, and driven entirely by how much sunlight hits which part of the surface at what angle. But 3I Atlas doesn't behave that way. Its hotspots are too localized, too discrete, and their activity doesn't correlate cleanly with the sun angle. Some vents turn on when they're facing the sun, which makes sense. Others turn on when they're in shadow, which does not. Dr. Petrov's explanation invokes cryovolcanism, a process where pressurized pockets of volatile ices, deep beneath the crust, suddenly flash to vapor, rupturing the surface and ejecting plumes of gas and dust into space. It's a process observed on moons like Enceladus and Triton, where tidal heating or residual radioactive decay provides energy to drive eruptions even far from the sun. But 3I Atlas is not a moon. It has no parent planet to generate tidal forces, and it's too small to retain significant radioactive heat. So what's driving the eruptions? The paper suggests 2 possibilities. First, trapped volatiles. If 3I Atlas formed in a very cold environment, perhaps in the outer regions of a protoplanetary disk around a dim red dwarf, it could have accreted highly volatile ices like carbon monoxide, methane, and nitrogen that remain stable at temperatures far below those that affect water ice. As the comet approaches the sun and warms, even slightly, these supervolatiles could reach their sublimation point deep inside the nucleus, building pressure until the crust fractures. Second, compositional layering. If the nucleus is a mix of ice-rich and rock-rich layers, different regions could have different thermal conductivities. Heat from the sun could penetrate unevenly, creating localized pressure buildups that vent through the weakest points in the crust. Both explanations are plausible. Both fit the data. But there's a third possibility the paper mentions only in passing, buried in the final paragraph of the discussion section. Alternatively, if 3I Atlas experienced a past close encounter with another star, or a planetary system, tidal stresses could have fractured the interior, creating pathways for volatile migration that remain active on geological timescales. Or, though the paper does not say this, something inside could be generating heat. On November 16th, a science journalist from Quanta magazine interviews Dr. Petrov over the phone. Your paper describes these hotspots as ice volcanoes. That's a strong term. Are you confident that's what they are? Dr. Petrov chooses her words carefully. Cryovolcanism is the best explanation we have that fits the thermal and spectroscopic data. The localized heating, the episodic outgassing, the dust composition, all of it points to discrete venting from beneath the surface. Whether you call them ice volcanoes or just vents is a matter of terminology. But volcanoes imply an energy source. Where is that energy coming from? That's the question we're still working on. Sublimation of supervolatiles is the leading candidate, but we can't rule out other mechanisms, such as a pause, residual heat from formation, tidal disruption during past encounters, even exotic chemistry involving reactive compounds. Comets are not simple objects. There's a lot we don't understand. Some people are speculating that the energy could be artificial. Some kind of power source on board. Dr. Petrov sighs, audibly. I've seen those theories. There is no evidence for artificial structures. The data is entirely consistent with natural geological processes. Ice volcanoes are strange, yes, but they're not impossible. We see them in our own solar system. but not on interstellar objects. This is the first interstellar comet we've been able to study in detail. It makes sense that it would surprise us. That's how science works. The interview is published on November 18th with the headline, Ice Volcanoes on the Interstellar Comet. What's powering them? The comment section explodes. One user writes, "Why are scientists so afraid to say, we don't know? If it doesn't fit the models, maybe the models are wrong." Another, "This is clearly a spacecraft venting propellant. Wake up." A third, more measured, "This is exactly why we need a mission to intercept these objects. Remote observation can only tell us so much." Meanwhile, behind the scenes, mission designers at NASA's Jet Propulsion Laboratory are thinking the same thing. On November 20th, a small team begins sketching out a concept study for a rapid response interstellar object interceptor, a spacecraft that could be kept in storage, fueled and ready, and launched within weeks of detecting an incoming object. The mission architecture is ambitious: ion propulsion for high delta-V, a modular payload bay for swappable instruments, autonomous navigation to handle the high closing speeds. The estimated cost, $800 million. The estimated development time, 5 years. The political likelihood of approval, low. But they sketch it anyway. Because someone has to. Because the next 3 in Atlas could arrive tomorrow, or in 100 years. And if we're not ready, we'll be left watching from 270 million kilometers away again, wondering what we're missing. On November 22nd, amateur astronomer Michael van der Merwe posts another image of 3 in Atlas. The coma is noticeably brighter, the tail longer, the whole structure more active than it was in October. In the stacked frames, he notices something new. Faint radial streaks emanating from the central condensation, like spokes on a wheel. He measures their angles. They're not evenly spaced. There are 6 of them, clustered in 2 groups. 6 vents. 6 hotspots. He cross-references Dr. Petrov's paper and realizes the streaks align with the thermal anomalies detected by Sophia. He's seeing the ice volcanoes. He posts the image with a caption, "Active venting clearly visible in tonight's data." This thing is waking up. The post gets 2,000 likes. One of the comments, "Looks like thrusters." Van der Merwe doesn't reply. He's learned to ignore the noise. But late that night, alone in his backyard under the South African stars, he stares at the image on his laptop screen and wonders. Because if you wanted to disguise a spacecraft as a comet, wouldn't you make it vent gas? Wouldn't you give it a coma, a tail, a natural appearance? And if you were clever, wouldn't you make the venting look random, chaotic, just irregular enough to seem natural? He closes the laptop and goes inside. Outside, 3E, Atlas continues its journey sunward, its surface warming, its interior shifting, and its 6 vents exhaling into the void. Whether those exhalations are the breath of an ancient frozen world or something more deliberate, no one yet knows. But the data is piling up, and the questions are multiplying faster than the answers. Continued in next response due to length constraints. Copy. Deep research. Yes. Continuing the 13,000-word script. Chapter 8, November 27th, 2025, when the pad failed. The failure happens at 9:47 UTC on November 27th, 2025. At Site 1/5 of the Baikonur Cosmodrome in Kazakhstan, the launch complex known formally as Gagarin Start, the same pad that sent Yuri Gagarin into orbit in 1961. And has launched every crewed Soyuz mission since. The launch itself is successful. Soyuz MS-27 lifts off perfectly, carrying 3 crew members, 1 Russian cosmonaut, 1 NASA astronaut, 1 SA astronaut, bound for the International Space Station. The rocket climbs cleanly, stages separate on schedule, and 9 minutes later, the crew capsule reaches orbit. Inside mission control, controllers exchange congratulations. The crew radios down. All systems nominal, feeling good, looking forward to docking. But on the ground, something has gone catastrophically wrong. The service platform, a massive steel structure that surrounds the rocket before launch and retracts seconds before ignition, has collapsed onto the pad. One of the hydraulic support arms, stressed beyond its design limit by decades of launches, metal fatigue, and inadequate maintenance, buckled during retraction. The arm fell, pulling part of the platform with it, and the structure crashed down onto the flame trench just as the rocket's engines were reaching full thrust. Superheated exhaust, normally channeled safely away through reinforced concrete ducts, spilled across the pad deck. Steel beams warped. Coolant lines ruptured. Fuel residue ignited. For 30 seconds, the launch complex was engulfed in flames. By the time the fire suppression systems activated, the damage was done. Roscosmos releases a brief statement at 11:15 UTC. Soyuz MS-27 crew successfully reached orbit and is en route to ISS. Launch pad infrastructure sustained damage during liftoff and is undergoing assessment. No personnel injuries reported. Nonetheless, the statement is calm, factual, and omits the most important detail. Site 1/5 is the only operational crewed-rated launch pad Russia currently has. And the next mission, Progress MS-29, a critical cargo resupply to the ISS, is scheduled for December 20th, 23 days away. By November 28th, engineers from Roscosmos, Energia, and the Russian Aerospace Forces are swarming the site. The initial damage assessment is grim. The flame trench has sustained structural damage, concrete cracked, rebar exposed, sections of the deflector plate melted. 2 of the 4 umbilical towers that provide power, fuel, and data connections to the rocket are non-functional, their cables severed by falling debris. The primary coolant system that protects the pad from engine heat is offline. And most critically, the service platform itself is twisted and jammed, unable to fully retract or extend. A full repair would take months. They have 3 weeks. On November 30th, a closed-door meeting convenes at Roscosmos headquarters in Moscow. Present, the head of Roscosmos, the chief designer of Energia, representatives from the Ministry of Defense, and the ISS program manager. The question, can the Progress launch proceed on December 20th? The chief designer is blunt. Not from Site 115. The pad will not be ready. Named fees. What are our alternatives? We have 2 options. First, delay the launch until February when repairs will be complete. Second, modify Site 31-6 at Baikonur to accept a Progress MS variant. Site 31-6 is a different pad, used primarily for uncrewed Soyuz launches carrying satellites and cargo. It has never launched a Progress spacecraft. The interfaces are different, the fueling procedures are different, and there are questions about whether the pad's telemetry systems can handle the real-time trajectory adjustments required for an ISS rendezvous. How long to modify it? 3 weeks, if we work around the clock. But there are risks. We've never done this before. And if we delay to February, the ISS has enough consumables to survive, but margins will be tight. The crew will have to ration water and reduce power consumption. Some experiments will need to be shut down. The ISS program manager shakes his head. That's not acceptable. We have visiting vehicles scheduled in January, spacewalks planned, international partners depending on that cargo. A long silence. We go with Site 31-6, the Roscosmos director says. Make it work. By December 2nd, crews are working 24-hour shifts at Site 31-6, welding new umbilical connections, reprogramming the pad's control systems, and running simulations to verify that a Progress spacecraft can safely launch from a facility never designed for it. The story leaks on December 4th. Thus, a Russian space journalist posts on Telegram, hearing that Progress MS-29 will launch from a non-standard pad due to damage at Site 150. If true, this is unprecedented and risky. The post is picked up by Western media within hours. A headline in Ars Technica. Russia scrambles to repair launch pad after Soyuz damage. IS resupply at risk. A headline in Space News. Roscosmos considers backup pad for critical December ISS cargo mission. NASA releases a carefully worded statement. We are in close communication with our Russian partners regarding the upcoming Progress resupply mission. The ISS crew is safe, well supplied, and prepared for any schedule adjustments that may be necessary. another eternity. But privately, NASA managers are nervous. The ESS operates on a finely tuned logistics schedule. Every visiting vehicle carries specific cargo time to arrive when it's needed. Progress, MS-29, is carrying replacement parts for the life support system, propellant for reboost maneuvers that keep the station from decaying out of orbit, and several time-sensitive experiments that missed earlier launches. If that cargo doesn't arrive, the station doesn't fail immediately. But margins shrink. Contingencies evaporate. The ISS becomes fragile in a way it hasn't been in years. On December 7th, the same night Earth passes beneath a bright Moon-Jupiter conjunction, and amateur astronomers around the world turn their telescopes toward 3E Atlas. A teleconference connects NASA's ESPS program office in Hughes' mission control in Munich, JAXA's operations center in Tsukuba, and Roscosmos mission control outside Moscow. The agenda: coordinate visiting vehicle traffic for late December and early January under multiple launch scenarios. If Progress MS-29 launches on December 20th and reaches the ESS on December 22nd as planned, the schedule holds. A Northrop Grumman Cygnus cargo ship can proceed with its planned January 9th launch. A SpaceX Dragon crew rotation mission can fly on January 24th. If Progress is delayed, everything downstream shifts. Docking ports become unavailable. Crew schedules conflict. Turn TV by human restaurant. Cargo delivery sequences break. The discussion is technical, methodical, and quietly tense. At one point, the NASA ES program manager says, half joking, "At least we don't have to worry about an interstellar comet hitting us." A few people laugh, nervously. Someone else mentions that 3I Atlas makes its closest approach to Earth on December 19th, one day before the Progress launch. Coincidence, someone mutters. Out here, everything's a coincidence until it's not, another voice replies. The meeting ends with a provisional agreement. Roscosmos will provide a final go, no-go decision for the December 20th Progress launch by December 15th, 5 days before liftoff. If the pad modifications are not complete or deemed unsafe, the mission will be delayed to January, and NASA will expedite a Cygnus resupply to fill the gap. Nobody is happy with the plan, but it's the best they have. On December 10th, engineers at Site 3106 complete the first full dress rehearsal. They roll a Progress simulator to the pad, connect the umbilicals, run through the fueling sequence, and simulate a countdown to T10 seconds. The pad performs flawlessly. On December 12th, they do it again. Another perfect run. On December 14th, they roll the real Progress MS-29 spacecraft to the pad. The vehicle sits on the pad, fueled and ready, while engineers double-check every connection, every sensor, every line of code in the control software. And overhead, invisible to the naked eye, 3I Atlas continues its approach, now just 5 days from its closest pass by Earth, its light curve pulsing every 16.16 hours, its ice volcanoes venting into the void, its backward curving tail defying simple models. Two machines from different worlds, one human-made, sitting on a damaged pad in the Kazakh steppe, waiting to deliver supplies to a space station 400 kilometers overhead. The other, a visitor from beyond the sun, drifting through the inner solar system on a hyperbolic arc, watched by telescopes and speculated about by millions. They share nothing except timing. December 19th, closest approach. December 20th, launch attempt. The sky does not care about schedules, about budgets, about the fragility of human spaceflight. But the people watching do. And they're running out of time. Chapter 9, December 7th, 2025, The Conjunction and the Quiet Vote. The Moon and Jupiter rise together on the evening of December 7th, so close in the sky that they appear almost to touch. Two bright spheres hanging low over the eastern horizon as twilight fades. For casual observers, it's a beautiful sight, simple and striking, the kind of celestial event that makes you stop and look up even if you're not usually the type to notice the sky. For astronomers, it's a headache. The full moon is one of the brightest objects in the night sky, and its light scatters through Earth's atmosphere, washing out faint sources, and making it nearly impossible to observe dim comets, distant galaxies, or anything else that requires dark skies. Ground-based telescopes, tracking 3 Atlas, have to work around the moon's glare, either observing before moonrise, after moonset, or using narrowband filters that block most of the scattered light. But the real challenge is not the conjunction itself. It's the meeting happening 12 hours earlier, in a secure video conference room connecting NASA headquarters in Washington, D.C., the Space Telescope Science Institute in Baltimore, the Jet Propulsion Laboratory in Pasadena, and ESA's European Space Operations Center in Darmstadt, Germany. The meeting is not on any public calendar. The agenda is listed simply as High-Value Transient Observation Planning, COA 4, 2025. 23 people attend, representing NASA's Astrophysics Division, ESA's Science Directorate, the Hubble and Webb mission offices, and several principal investigators from approved observing programs whose telescope time is about to be preempted. The topic: whether to redirect significant space telescope resources toward 3 Atlas during the critical December 15th, 22nd window, and if so, whose approved observations will be delayed or canceled to make it happen. Dr. Marcus Delgado from JPL presents first. He puts up a slide showing 3 Atlas's trajectory, highlighting the narrow geometry window when Earth, the comet, and the Sun will be positioned optimally for parallax measurements, spectroscopy, and multi-wavelength observations. This is the best chance we'll have to study an interstellar object in detail for at least another 5 to 10 years, he says. Maybe longer. The science return is enormous: composition, structure, surface properties, outgassing dynamics. But the window is tight. After December 22nd, the comet's heliocentric and geocentric geometry degrade rapidly. It becomes fainter, harder to track, and inaccessible to radar. He clicks to the next slide. A requested observing schedule. Hubble. 18 additional orbits, split between high-resolution imaging and UV spectroscopy. James Webb. 14 hours across NIRSPEC, MIRI, and NIRCam, targeting ice and organic absorption features. Chandra. 60 kiloseconds, contingent on X-ray detection, to search for high-energy emission from charged particle interactions. The slide also includes a request for priority scheduling on the Very Large Array, Gemini North and South, and the European Southern Observatories VLT, though those are ground-based and technically outside this committee's jurisdiction. Dr. Delgado sits down. The room is silent. The Hubble program scientist speaks first. 18 orbits is a significant ask. We have 14 approved programs scheduled during that period, including time-critical supernova follow-up and a deep field survey that's been in the queue for 9 months. If we bump those, we're looking at delays that cascade into Q1 2026. How time-critical is the supernova follow-up? Someone asks. Very. It's a type Ia that just peaked. If we don't observe it now, we lose the data. Can we split the time? Give 9 orbits to 3 Atlas and keep the supernova program? Then both programs are compromised. Dr. Naomi Hart from STCI interjects. The last time we had an interstellar object, we missed it. Oumuamua came and went, and we barely got a few pixels. Borisov was better, but we still didn't have enough time to do the full suite of observations. This is the third one. We can't afford to miss it again. Science is always about trade-offs, someone else says. We're not saying 3 Atlas isn't important. We're saying there are other important things too, and we can't just ignore them. A Webb mission planner speaks up. Webb is even tighter. We have less scheduling flexibility than Hubble. 14 hours means displacing at least 3 approved GoPrams, possibly more. And Webb time is hard to get back. Our oversubscription rate is 8 to 1. What if we use director's discretionary time? That pool is nearly exhausted for the year. We'd be borrowing against next year's allocation. The debate continues for 40 minutes. Data rates, science priorities, political optics, international partnerships. Some argue that 3A Atlas is a once-in-a-decade opportunity that justifies the disruption. Others argue that abandoning approved programs undermines the peer review process and sets a dangerous precedent. Finally, The NASA Astrophysics Division Director, sitting in his office in Washington, his face framed in a small video box on everyone's screen, speaks. Let's be practical. We're not going to cancel existing programs outright. But we can propose a compromise. We'll allocate partial time to 3i Atlas using director's discretionary, and we'll request that impacted PIS voluntarily defer their observations with guaranteed priority, rescheduling in Q1. We'll also coordinate with ESA and the ground-based facilities to maximize coverage across the network, so we're not entirely dependent on Hubble and Webb. Yeah. Ooh. He pauses. But I want to be clear. This is a high-visibility target. If we don't observe it adequately and something significant is discovered later by another facility, we will be asked why NASA didn't prioritize it. Understood? The room nods. Good. Let's draft a coordination plan and have it ready for approval by December 10th. The meeting ends. Within 24 hours, emails go out to affected principal investigators. The tone is apologetic but firm. Due to an urgent, time-sensitive transient observation opportunity, we are requesting a voluntary deferral of your approved observing program scheduled for December 15. 22. Your program will be given absolute priority for rescheduling in early 2026. Most of the PIs agree. A few push back, arguing that their science is equally time-critical. Quiet negotiations happen over email and phone calls. Compromises are reached. By December 9th, the observing schedule is locked. Hubble will observe 3A Atlas on December 16th, 18th, and 20th. Webb will observe on December 17th and 21st. Ground-based facilities will fill the gaps in between, weather permitting. And alongside the official coordination, a quieter effort is underway. NASA's Planetary Defense Coordination Office, in coordination with the Deep Space Network, tasks 3 radar dishes, Goldstone in California, Arecibo's successor facility in Puerto Rico, and the European Space Agency's dish in Australia, to attempt radar imaging of 3 Atlas during closest approach. Radar is tricky for a fast-moving distant target. The comet will be near the limit of detectability, and the return signal will be weak, noisy, maybe unusable. But if it works, radar can reveal the nucleus's shape, rotation state, and surface roughness in ways that optical telescopes cannot. The request is marked priority scheduling, time critical. Other radar programs are quietly bumped. On Mars, mission planners for the HiRISE camera aboard the Mars Reconnaissance Orbiter submit a target of opportunity request to image 3 Atlas as it crosses the Martian sky. HiRISE normally photographs the Martian surface. Pointing it at a comet is unusual, but not unprecedented. The request is approved. On the surface of Mars, the Perseverance rover's science team is asked whether Pixel and Sherlock, spectrometers designed to analyze rocks, can be used to sample dust particles settling through the atmosphere that might have originated from 3 Atlas. The answer is maybe, if the dust flux is high enough, and if the particles are large enough to settle rather than stay suspended indefinitely in the thin Martian air. It's a long shot, but the team agrees to try. And at the Very Large Array in New Mexico, radio astronomers quietly schedule round-the-clock observations of 3I Atlas from December 18th through December 22nd, watching for any change in the 16.6-hour radio pulse, any anomalous emission, any hint of structure beyond a simple rotating nucleus. None of this appears in press releases. None of it is discussed on NASA's public social media feeds. But behind the scenes, the global astronomical community is quietly mobilizing, coordinating, and preparing for what may be the most intensely observed week in the history of cometary science. On the evening of December 7th, as the Moon and Jupiter hang together in the sky, Dr. Naomi Hart stands outside the Space Telescope Science Institute in Baltimore, looking up. She knows the schedule. She knows what's been sacrificed to make this happen. She knows that in 10 days, Hubble will turn toward 3I Atlas and capture images that might answer lingering questions or raise new ones. She also knows that in scientific research, answers are rare when questions multiply. A colleague joins her outside, coffee in hand. "Think we'll find anything?" he asks. Dr. Hart shrugs. "We'll find something. Whether we'll understand it is a different question." They stand in silence for a moment, watching the moon climb higher. Somewhere out there, beyond the moon, beyond the fading Geminids, an interstellar visitor is approaching. And the countdown has begun. Chapter 10. December 13th, 14th, 2025. The Geminids and the Ghost. The Geminid meteor shower peaks on the night of December 13th, 2025, and it does not disappoint. Under dark skies, far from city lights, observers can see up to 120 meteors per hour. Bright streaks of light cutting across the constellations as Earth plows through a river of debris left behind by asteroid 3200 Phaethon. The Geminids are one of the most reliable showers of the year, and this year, with the moon setting early, the viewing conditions are ideal. Across 6 continents, amateur astronomers set up cameras, reclining chairs, and thermoses of coffee, settling in for a long night of sky watching. But this year, they're not just watching for meteors. On astronomy forums, in Discord servers, and across social media, the word has spread. If you're out for the Geminids, point your camera at 3 Atlas II. The comet is still faint, around magnitude 12, too dim for the naked eye. But it's well within reach of backyard telescopes and DSLR cameras with telephoto lenses. And the amateur community has organized. The 3i Global Watch campaign, coordinated by a loose network of amateur astronomers and citizen scientists, aims to provide continuous photometric coverage of the comet from December 13th through December 22nd, filling gaps between professional observations and catching any short-term variability that might be missed by scheduled telescope time. More than 200 observers in 40 countries have signed up. On the night of December 13th, as meteors streak overhead, those cameras are also locked onto 3 Atlas, stacking exposures, measuring brightness, and uploading data to a shared archive. By dawn on December 14th, the first light curves start appearing in the community data pipeline. And something strange shows up. Michael van der Merwe in South Africa is the first to notice. He's been tracking 3 Atlas for months now, and he knows its light curve by heart. A smooth sinusoidal pulse repeating every 16.6 hours, like clockwork. But in his December 13th data, there's a secondary fluctuation. It's subtle, barely 2% of the total brightness. But it's there, a small dip about 4 hours after the main brightness peak, followed by a small bump 4 hours before the next peak. The timing is too regular to be noise, but it doesn't match the rotation period. He checks his calibration, reprocesses the images. The feature persists. He posts it to the 3i Global Watch forum, seeing a possible secondary modulation in last night's data. Can anyone else confirm? Within 6 hours, 3 other observers reply. 1 in Chile, 1 in Australia, 1 in Spain. All 3 see the same thing, a faint, repeating fluctuation offset from the main 16.1 6-hour pulse. By December 14th, someone runs a Fourier analysis on the combined dataset. The secondary signal has a period of approximately 8 hours, exactly half the primary period. A harmonic. That makes sense if the nucleus is elongated and rotating. You'd see 2 brightness peaks per rotation as the long axis swings in and out of view. The fact that one peak is stronger than the other just means the nucleus isn't perfectly symmetric. But here's the problem. The harmonic wasn't there in October or November. It only appears in the December data. Which means either A. The comet's rotation state has changed, maybe an outburst. A large jet, or a fragment breaking off, has altered its spin. B. The viewing geometry has changed enough to reveal a feature that was previously hidden. C. Something new has turned on. Dr. Amara Okonkwo, who first identified the 16.16-hour period back in October, downloads the amateur data and runs it through her own analysis pipeline. She confirms the harmonic. On the evening of December 14th, she emails Dr. Hu. Michael Zhao, the light curve is evolving. We need to get more professional data during closest approach. If this is real, it could mean the object is more complex than we thought. Dr. Zhao forwards the email to the Hubble scheduling team with a request. Can we add a high-cadence imaging sequence on December 19th to capture any short timescale variability? The response comes back within an hour. Already planned. We'll have continuous coverage from 12:00 to 18:00 UTC on the 19th. Nedi. Nudit. Meanwhile, the Geminids continue. On the night of December 14th, the meteor rate drops slightly as Earth moves past the densest part of the debris stream. But the sky is still active. Bright fireballs occasionally light up the atmosphere, leaving glowing trails that persist for seconds. And through it all, 3i Atlas drifts silently through Sagittarius, now less than 6 days from closest approach, its coma visibly brighter than it was a week ago, its narrow tail stretching southward like a faint brushstroke against the Milky Way. A photographer in New Mexico captures a time-lapse sequence showing both meteors streaking across the frame in rapid bursts, and 3i Atlas moving slowly, steadily, frame by frame, a ghostly presence among the fireworks. The video is posted online with the caption, Geminids and the Interstellar Visitor, December 14th, 2025. It's shared 18,000 times. One of the comments, the meteors are from our solar system. The comet is not. And it's getting closer. Another, anyone else think the comet looks like it's pulsing in this footage? The photographer replies, that's not the comet pulsing, that's the stacking algorithm trying to track a moving target. But yeah, it does look eerie. But when Dr. Okonkwo sees the video, she pauses it, zooms in, and measures the brightness of the comet in each frame. The pulsing isn't just an artifact. The comet is brighter in some frames than others, and the pattern, when she times it against the video metadata, matches the 8-hour harmonic she's been tracking. She saves the video, adds it to her growing archive of 3i Atlas data, and makes a note. High-frequency variability confirmed in independent visual data. Not instrumental. Show. On the morning of December 15th, a preprint appears on ArcSave from a team at Lowell Observatory, emerging 8-hour photometric modulation in interstellar comet 3i Atlas, evidence for binary nucleus or complex spin state. The paper is short, preliminary, and careful, but it asks the question directly, is 3i Atlas a single object, or two? Binary comets are rare but not unknown. Sometimes a comet's nucleus splits into 2 or more fragments, either during a close pass by a planet or due to rotational stress. If 3i Atlas is a binary, the 2 components could be orbiting each other every 8 hours, creating the secondary brightness modulation as they eclipse and reflect light off one another. Alternatively, the nucleus could be a single object in a complex rotation state, tumbling chaotically rather than spinning smoothly, which can produce multiple periodicities in the light curve. The paper concludes, high-resolution imaging during closest approach on December 19th will be critical to distinguish between these scenarios. By December 15th, the global astronomy community is fully focused on the coming week. Observing schedules are finalized. Weather forecasts are checked obsessively. Backup plans are drafted in case of clouds, equipment failure, or satellite interference. And in homes and backyards across the world, amateur astronomers prepare for another night of observation, their telescopes aimed at a faint green-white speck moving slowly against the stars, a visitor from another system that, for a few brief days, is closer to us than it will ever be again. On the evening of December 15th, Michael van der Merwe steps outside into the warm South African summer night, his telescope already aligned and tracking. He looks up at the sky, clear, dark, filled with stars, and thinks about the fact that somewhere out there 200 million kilometers away, an object the size of a small mountain is falling toward the sun, and we are watching it in real time, frame by frame, pulse by pulse. He opens his laptop, cues the imaging sequence, and lets the camera run. Outside, the Geminids have faded. The moon has set. The sky belongs to the stars. And the ghost in Sagittarius continues its approach, steady and silent, carrying questions we are only beginning to ask. Chapter 11, December 18th, 2025, countdown at 270 million kilometers. December 18th, 2025. Feels like the night before a launch. Except the thing approaching isn't ours, and we can't control it. Across the world, observatories are running final checks. In Baltimore, the Hubble Space Telescope operations team reviews the timeline for tomorrow's observation sequence. 6 hours of continuous tracking, switching between filters, exposures time to capture every phase of the comet's rotation. In California, engineers at the Deep Space Network's Goldstone complex are calibrating the 70-meter radar dish, preparing to bounce radio waves off an object moving at 60 kilometers per second relative to Earth. In New Mexico, the Very Large Array is locked in position. 27 radio antennas pointed at a single patch of sky in Sagittarius, waiting. And in hundreds of homes, backyards, and small observatories scattered across 6 continents, amateur astronomers are checking weather forecasts, testing cameras, and uploading the latest photometry to shared databases. Everyone is watching the same countdown. 24 hours until closest approach. On NASA's website, a public-facing tracker page shows 3I Atlas's position in real time. Distance from Earth, distance from the Sun, current velocity, estimated brightness. The page has been live for weeks, but traffic spikes on December 18. By evening, the page is receiving 40,000 hits per hour. A live discussion thread on Reddit's r/astronomy forum has more than 3,000 comments. People are posting images, speculating about what tomorrow's observations might reveal, and sharing telescope setups. One user writes, "This is the closest we'll ever get to touching something from another star without leaving the solar system. Crazy to think about." Another, "Still can't believe we're getting all this data and no mission. We should have sent a probe." A third, "There wasn't time. We didn't know it was coming until July. You can't launch an interplanetary mission in 6 months." A fourth, "Unless it's not a comet." The thread branches into the usual debate: natural versus artificial, science versus speculation, but the tone is different now. There's less mockery, more genuine curiosity. The data has piled up over 5 months. The carbon-rich composition, the 16.16-hour pulse, the ice volcanoes, the secondary 8-hour modulation, the backward tail. No single anomaly is conclusive, but together, they've created a pattern that even skeptics admit is unusual. And tomorrow, we'll have the best data yet. At 18:00 on December 18, Dr. Naomi Hart convenes a final pre-observation teleconference with the Hubble team. The agenda: review the observation plan, confirm target coordinates, discuss contingencies. Target position is solid, someone reports. Ephemeris updated with the latest astrometry from Gemini and amateur networks. Uncertainty is less than 0.1 arcseconds. Weather? Clear skies predicted for the ground-based sites. No solar activity expected that would interfere with communications. Chennai. Data handling? Will be downlinking in real time via TDRSS. First images should be available for quick look within 2 hours of observation. Dr. Hart nods. Okay. Let's remember, this is a 6-hour window. We won't get another chance like this. If something unexpected happens, an outburst, a brightness spike, anything, we have some flexibility to adjust the sequence on the fly. But it has to be a fast decision. Everyone clear? The team confirms. Good. Let's make it count. The call ends. Dr. Hart leans back in her chair and stares at the schedule on her screen. 6 hours. 400 minutes. Thousands of images. And somewhere in those images, an answer to the question that's been nagging at her since August. What is that secondary brightness not in the coma? She's seen it in every Hubble observation since the first one. It moves, but not like a separate object. It pulses, but not randomly. It's always there, offset from the nucleus, persistent and unresolved. Tomorrow, with 3A Atlas at its closest, Hubble's resolution will be at its best. If the knot is a discrete clump of dust, it should resolve into a diffuse cloud. If it's a fragment or a moonlet, it should separate from the main nucleus. And if it's something else, she doesn't let herself finish the thought. At the Jet Propulsion Laboratory in Pasadena, Dr. Marcus Delgado is running trajectory simulations one last time. He's modeling 3I Atlas's orbit forward, through the close approach and beyond, checking for any perturbations, any tiny deviations from a purely gravitational trajectory. If the comet has jets, active venting that creates thrust. They could alter its path slightly, a phenomenon called a non-gravitational acceleration. It's common in comets. Gas venting from the sunward side pushes the nucleus like a tiny rocket, changing its orbit in measurable ways. But 3A Atlas's jets, if they exist, are strange. The thermal hotspots don't align with the sun angle. The light curve periodicities suggest something more structured than random outgassing. Dr. Delgado's simulation includes a term for non-gravitational forces, estimated from the observed brightness and assumed gas production rate. The result: 3 Atlas's trajectory should deviate from a pure Keplerian orbit by roughly 200 kilometers over the next 48 hours. That's tiny, less than the width of the comet's coma, but it's measurable. If tomorrow's radar observations can pin down the nucleus position to within a few kilometers, they'll be able to see if the comet is being pushed by its own outgassing, or by something else. He saves the simulation, uploads it to the shared server, and sends an email to the radar team. Here's the predicted position for 19:00 UTC tomorrow, with uncertainty bounds. Let me know what you get. Across the Atlantic, at the European Space Agency's Operations Center in Darmstadt, mission planners are coordinating the Mars-based observations. The Mars Reconnaissance Orbiter will image 3 Atlas during a brief window when the comet passes through the spacecraft's field of view. It's a long shot. MRO's high-rise camera is designed for surface imaging, not astronomical targets. But if it works, it will provide a different viewing angle, helping to constrain the comet's three-dimensional structure. On the surface, Perseverance is running an experiment. Sherlock, the rover's ultraviolet spectrometer, will analyze airborne dust samples collected by the rover's wind sensors. If any dust from 3 Atlas has made it to Mars, drifting across tens of millions of kilometers before settling through the thin Martian atmosphere, it could carry chemical fingerprints distinct from Martian material. The odds are low. The dust flux from the comet is faint, and Mars is not directly downstream from the comet's tail. But sometimes in science, you get lucky. At 21:00 UTC, the sun sets over the Very Large Array in New Mexico, and the night shift begins. Radio astronomer Dr. Lisa Kwan is on site, coordinating the 48-hour observation campaign that starts tonight and runs through December 20th. The VLA is configured in its most compact arrangement, optimizing sensitivity for faint sources. All 27 antennas are phase-locked, combining their signals to act as a single giant dish with an effective diameter of several kilometers. The target: 3 Atlas, at 21 centimeter wavelength, listening for radio emission from charged particles, molecular gas, or anything else that might radiate in this part of the spectrum. Dr. Kwan pulls up the preliminary data from earlier test observations. The signal is faint, noisy, but detectable. And there, buried in the static, is the 16.16-hour modulation, visible not just in brightness but in the radio spectrum itself. Whatever is creating that pulse is affecting both visible light and radio waves. She makes a note: if we see any deviation from the 16-hour period during closest approach, flag it immediately. By midnight UTS, early evening in California, morning in Australia, telescopes across the world are turning toward Sagittarius. The global campaign is beginning. And 270 million kilometers away, 3 Atlas continues its fall toward the sun, unaware of the hundreds of instruments tracking it, the thousands of people watching it, the millions of lines of code processing its light. It moves at 60 kilometers per second, fast enough to cross the distance from Earth to the Moon in less than 2 hours. But on cosmic scales, it is slow, patient, tracing an arc through the inner solar system that was determined billions of years ago by gravitational interactions we will never know. On the night of December 18th, Dr. Amara Okonkwo sits in her office at the University of Maryland, staring at the light curve she's been building for 3 months. The data is beautiful in its own way. A perfect sine wave, 16.16 hours, repeating 63 times without drift, without variation. And now, overlaid on it, the new 8-hour harmonic, emerging like a whisper in the noise. She wonders what tomorrow will show. An outburst? A fragment? A resolved companion? Or just more questions, stacked on top of the ones we already have? She closes her laptop, stands, and looks out the window at the winter sky. Out there, somewhere above the horizon, too faint to see but bright enough to measure, an interstellar visitor is approaching. And tomorrow, for a few hours, we will see it more clearly than ever before. Or at least, we will try.